All right, so we did a lot of tests, right? And here's a challenge. Can you remember all the tests?
What?
Give me all the tests that you know.
N series, P series, geometric.
Okay, no, one by one. One by one. Okay.
We should have a root test.
Root test. Okay. Root test.
Ratio.
Yeah. Okay. Root test and ratio test. Let me.
P test.
Wait. Root test and ratio test. So what is this? Here R is limit of n going to infinity of nth root of absolute value of an, right? Here R is limit n going to
an
infinity.
plus 1 over 1. N.
Yes. Oh, that's good. All right. So you have criteria for each case. If R value is less than 1, what do we know?
It converges.
Yeah, the series summation of an converges. Right? If R is equal to 1, what do we know?
We don't know.
Yeah, it's inconclusive. Inconclusive is n. And then if R is bigger than 1, diverges. Okay, good. And then somebody mentioned P test or P series. What is this about?
If P is greater than 1.
Right. It's about the P series, a series of this form, 1 over n to the p power. And if P is less or equal to 1, it diverges. And then if P is greater than 1, it converges. Okay, what else?
Geometric.
Comparison, okay. All right, so let's write geometric first. Geometric series. It's like, but I don't even want to write the criteria for this because, let's just write down the results. So this would be A over 1 minus R if R is between this, and then otherwise it diverges, right? Yeah, let me not write everything. Okay, so okay, somebody said comparison test before. Okay, so comparison test. Well, this, and then the limit comparison test, right? There's the limit comparison test.
Ultimate series.
Very good.
Telescope.
Okay, all right, just give me some time to write down. All right, so comparison test, what is this about? Well, it's about the fact that if you have something positive, let's say an and bn's are both positive, and if an is less than bn, then the summation of an should also be less than summation of bn. That's basically the idea. But the way you use it is like, if the summation of an is infinity, and bn is bigger than an, what do we know about summation of bn? It must be infinity as well, right? Okay, and vice versa. If you know that bn is some convergent series, it gives you some finite value, then since an is less than bn, we know that summation of an must be finite as well. It must be convergent as well. So that's the way you use it. Often this is not the one that you want to use because it's hard to prove inequalities. Inequalities are harder than equalities. So you want to avoid that as much as possible. So instead of that, we like to use the limit comparison test. What is this about? Again, they both have this condition. What is this about?
You compare the limits.
You take the limit and going to infinity, you compare the two at infinity. When n is really large, you want to see whether the two things are comparable. And by comparable, I mean that it should equal to some value of L, which is a non-zero value. So when n is really big, one is like some multiple of the other. In that case, the summation of an follows the convergence or divergence of summation of Bn, right? So if this converges, this converges. If this diverges as well. And often you want to choose some simple ones that you know the convergence of. So those simple ones are usually a P-series or geometric series. That's why these provide some building blocks. Okay, now tell me the other ones that you said. Alternating series test, okay. Alternating series test.
Harmonic.
And then somebody also said absolute convergence test.
Telescoping.
Harmonic.
Okay. Yeah, I got you. I'll say that again. Okay. All right, so alternating series test. This has two conditions. Do you remember the two conditions?
It has to not be
K equals 0.
No.
Oh, K equal 1.
Limit as n goes to infinity of the sequence has to be 0. And we also had another condition. an plus 1 had to be less than an, meaning that the sequence has to be decreasing. And here I'm still assuming that an is positive. If these two conditions are met, then the summation of the alternating series, this negative 1 to the nth power makes the signs flip positive, negative, positive, negative. That's what alternating series means, right? This converges. Okay. Who can tell me what absolute convergence test is?
If it's conditionally or if
No.
in some cases.
If the absolute value converges, then the one without the absolute value converges as well. So absolute convergence test says that if summation of absolute value of an converges, then summation of an converges as well. And we did talk about conditionally convergent and absolutely convergent. So if this converges, we say this series absolutely converges. But there are cases where this converges but this doesn't, and you can prove its convergence using alternating series test. And if this converges while this does not, then we call that conditionally convergent. And the distinction was important because if some series is conditionally convergent, then you cannot switch the order of summation, so you have to be really careful. Okay. All right, then some people said telescoping. But you know what? When it comes to testing something for convergence or not, this rarely comes into play. So, I mean, sometimes you can notice something's a telescoping, but they rarely come into play. So I'm not going to talk about that. Was there something else? Yeah, someone told me something, I forgot.
Oh, harmonic.
Harmonic series, okay, yeah. So harmonic series.
Harmonic.
What about harmonic series?
I don't know, 1 over n.
That's an example of harmonic series. Okay, so what do we know about harmonic series? It always diverges, yes. Okay. And then I don't think people mentioned these two, but those were like very early on, so I think that's why you forgot them. So one is integral test.
And
P-test we did.
what about nth term?
Nth term test. Yes, very good. Nth term test.
Wait, there's way too many, yeah.
And this is like
We're taking a test on tests.
yes, you're taking a test.
That's
on this.
terrible.
Yeah. This is also known as test for
Test
divergence. Okay, so integral test is that you have integral of f of x dx from a to infinity, whether this converges or not determines the summation from n equals to a to infinity of fn. So an example of this is like we use the integral test to show the p-test, right? When we wanted to know whether 1 over n squared converged or not, what we did was we replaced n by x, and we just integrated from 1 to infinity and showed that this gives you a finite number. And because this converges, we show that this converges as well. That's how we use the integral test. However, there's some condition here, which is that you don't want this to be like fluctuating wildly, because what we're doing is we're just sampling this at integer points, but this one takes into consideration all the values from 1 through 2. There are infinitely many values from 1 through 2, right? Here, you only talk about 1, 2, 3, 4. But here, you're considering all the values in between. So if the values in between is like wildly behaving, we can't use that comparison. So there's a condition about fx being monotonically decreasing to 0. So that's an extra condition. I'm not writing it. Like, see, the things I'm writing here is very crude. It's very rough. There's some additional things that I'm not writing here. So you have to solve problems to know those fine points about these tests. Okay. All right, and then the nth term test. What is this?
Test for divergence. When they
Yeah.
both are the same.
No. If the limit of an as n going to infinity is not 0, what do we know? Summation of an diverges. Okay? It's very common to forget that if the limit of an goes to 0, this test does not mean that it converges. Okay? This is called test for divergence because you can only apply this rule when the conclusion is diverges. Okay? So maybe you might want to add here that if limit n going to infinity of an is equal to 0, then the test is inconclusive. Okay. Sometimes it might converge, sometimes it might not. Okay? So that's what nth term test does.